Hello everyone, this is Matheus Rosa from the University of Colorado Boulder. I'm a PhD student advised by Dr. Massimo Rosini, and today I'll be talking about the manipulation of localized modes in elastic media via twisting. So the motivation for this work is in the recent interest for Moiré patterns and twisted bilayer systems in the emergent field so-called twistronics. So one example is given in this figure here of a bilayer graphene lattice that is composed by two graphene sheets that are twisted with respect to one another. And research has shown a series of remarkable properties that emerge from the twisting of these two systems, in particular, in this case, unconventional superconductivity. Another example that I would like to mention is this work in photonics, where they have two twisted square lattices in the form of continuous modulations, and the authors talks about localized modes in the photonic lattice. So in this context, we have begun to explore the twisting as an interesting degree of freedom in mechanics as well. And this first work was done in collaboration with Dr. Emil Prodan. So what we did in this case is, instead of having two physical lattices that are twisted with respect to one another, we have a single lattice of mechanical resonators and a twisted potential that defines the interactions of the resonators. So the lattice is fixed in space, and we can think of the potential being twisted with respect to the lattice, forming Moiré patterns for particular angles. And one of the results that we've shown is if you map the spectral properties of this lattice as a function of twist angle, you find interesting Hofstadter-like butterflies, and these gaps are topological gaps with topological properties similar to the for the quantum Hall effect. In this work in particular, I would like to mention a few interesting things that may happen for a fixed rotation angle on your system and the emergence of localized modes. And I will also go to continuous elastic systems instead of discrete mechanical resonators. So this is a brief outline of this talk. First, I will introduce the continuous twisted modulations that we will consider, and then how these modulations lead to localized modes in elastic plates. And then I will describe how the regions of these localized modes can be manipulated through phason trajectories. Following these numerical illustrations, I will touch on some preliminary experimental results on pillared plates. And finally, I will follow with the conclusions. So I would like to start by showing how we build twisted modulations in a continuous setting, and we'll apply them to elastic plates. So we take a first square lattice type modulation that is a continuous just a superposition of two perpendicular sine waves, and you can see the square lattice pattern. And we superimpose an identical modulation which is twisted by theta with respect to the first one. And then that gives us a continuous modulation function that resembles Moiré patterns in a square lattice setting. The system of choice for which I'll illustrate the properties is a simple elastic plate governed by Kirchhoff equations, and we take a homogeneous plate on an elastic foundation, and the stiffness of the elastic foundation will be given by our twisted modulation functions. So to illustrate the emergence of localized modes, we touch briefly on how the modulation of the ground stiffness is built. In particular, we note that there is a DC component such that there is no negative stiffness, and two main components, the first one being this fixed square modulation with amplitude P1, and the second one is the twisted square modulation with an amplitude P2 that we allow to vary. So if we compute the modes of a finite plate for a fixed twist angle and a fixed amplitude P1, as a function of P2, we see interesting mode transitions. So in this figure, each eigenfrequency is color-coded by a polarization factor, which is called the inverse participation ratio, and it signals if the modes are localized or not.
So for low P2 values, there are no localized modes because this is the regular periodic lattice with a square wave modulation. As we increase P2, we see interesting mode transitions and some modes becoming localized as we increase the amplitude of the twisted component. So for example, if we track one of these branches, we can see that initially the mode is a global bulk mode vibrating in the entire plate. Then as you increase P2, it slowly becomes localized in the interior of the plate as shown in these figures. So to illustrate how we can manipulate the regions of where the modes become localized, we talk about the phason degree of freedom. So to illustrate, let's take our initial square wave modulation, superimpose it to the twisted component to create our Moiré pattern, and then we can see that we can slide one modulation with respect to the other one, and this gives us the phason degree of freedoms. In particular, there are two components, the phason associated with the sliding along x, so phi x, and the one along y, phi y. And I would just briefly remark that the space formed by these 2 degrees of freedom is a 2-dimensional torus, and this is why we obtain topological properties akin to the 4-dimensional quantum Hall effect, because we have the 2 dimensions associated with space plus 2 extra dimensions in this 2-dimensional torus associated with the phasons.
So we can now compute the modes of the plate as a function of one of the phason parameters phi x, for example, and we find that there is a band gap and a mode that spans the band gap, and this is a topological edge state, as shown in previous papers. But in this case, what is interesting is the transition experienced by this edge state. So as the animation shows, it starts localized at the left boundary, and then as it merges within the bulk bands, it becomes localized in the interior of the plate. And if you follow the mode, it slowly translates across the plate, and when it reaches the other branch of the edge state, it will become localized at the right boundary. So it's a transition of the edge state from being localized to the left to the right that occurs as a localized mode in the interior of the plate. So these localization transitions have interesting opportunities when we think about the entire phason space of both the phi x and phi y variable. So for example, if we start with the mode localized in the center of the plate, we can choose trajectories on this space to manipulate the regions where these modes are localized. This is one example where it follows the path by these 2 red curves, and there are other possibilities as well, as described in the next slides. In this second example, we consider the square path on the phason space, and if we follow the mode along this path, we can see that the mode shape remains localized and moving along the region defined similarly to the path. One can consider even more complex trajectories, and this is a final example of a spiral taken in the phason space, and then we can see the mode evolving according to a spiral path as well. So finally, I would briefly touch on a few experiments that we have been doing. We go from a continuous modulation setting to a discrete lattice setting on a plate with pillars. So the pillars are arranged according to a fixed square lattice, but the heights of the pillars are modulated according to a twisted modulation function, similarly to the lattices that were previously described. And this is one example of a 3D printed plate following this pattern. Here are a few experimental results that we've got with this initial plate. These fields are measured by a laser vibrometer, and if we look at some of the peaks in the frequency response, we can find modes that are localized at the center of the plate. In the future, we wish to build many more plates to look at the phason trajectories and see if these modes can move around in the plate according to the designed phasons.
So to summarize, these results illustrate how twisting and sliding are interesting degrees of freedom for continuous or lattice type modulations in elastic media to create and manipulate localized modes.
Finally, I would like to acknowledge support from our funding agencies and also thank my advisor Massimo Roseni And thank you all for listening.